Hi, my name is Akshay Kumar. I'm a non-trivial fellow. I'll be talking to you today about my project, which is a workflow for the rapid design of siRNAs targeting viral CREs, a study in dengue. Okay, so advances in biotechnology have improved pathogen manipulation and understanding, but they've also increased the potential for the creation and/or release of highly virulent strains of viruses. Engineered and natural pathogens pose a significant global health threat with the potential to cause catastrophic pandemics. Experts predict between a 1.8 to 3.85% chance for one of these pandemics to occur within the next century, which is a relatively high probability for an issue of this caliber. These pandemics could severely disrupt social and economic systems, overwhelm healthcare infrastructure, and result in widespread illness and death. The rapid transmission and far reaching impact of potential emerging pathogens highlights the need for effective and adaptable strategies for pandemic prevention and rapid response. While traditional drug development lacks the flexibility needed for rapidly spreading or evolving diseases, broad spectrum approaches targeting key viral mechanisms could be essential to mitigate the impact of future outbreaks. These approaches could optimize treatment development in times of crisis, greatly aiding pandemic response. In this project, I designed a computational biology workflow to produce and validate siRNA molecules targeting cis-acting RNA elements in the virus genome by making use of freely available web servers and data. Cis-acting RNA elements, or CREs, are structures in a virus's untranslated region that are heavily conserved and integral for virus function. The flexible nature of the workflow and the conserved nature of the CREs should ensure that this approach can be taken with any emerging pathogen to produce broad-spectrum antivirals. I tested this approach by studying dengue, which was picked due to having four serotypes and limited treatment options. Dengue manifests in around 96 million people yearly, and of those cases, fatality rates have been estimated to range from 1 to 5%. There is no universal treatment for dengue, and the virus's public health burden is only increasing. If identified siRNAs are effective across the four serotypes of dengue, they would then exhibit broad spectrum capabilities beyond simply the flexibility of the workflow. So, why am I doing this project? Well, I picked this problem because I believe I'm uniquely suited to solve it. I've conducted computational and biological research separately before. Applying what I've learned from my past research allowed me to synthesize this interdisciplinary project while taking into consideration both computational and biological principles, which is relatively rare amongst researchers. Additionally, this project is effectively about optimizing resource and time allocation via the use of technology. Conducting this research would support my success in my future career in research management. I want to be at the forefront of research optimization, directly studying how to improve our approach to science. This project is a solid stepping stone on that path. Okay, so this is a workflow I actually used. I essentially selected a dengue serotype, identified all potential siRNAs for that serotype, and then run a gamut of tests in order to narrow down that initial list to the siRNAs with the most potential. 11 potential siRNAs were initially identified. Of those 11, S6, S8, and S11 were shown to be the most promising siRNA molecules developed. These siRNAs showed optimal stability and efficacy, showed conservancy across the serotypes with minimal off-target risk, and showed a strong interaction with the cellular machinery that performed the silencing siRNA are known for. These results highlight the effectiveness of the computational workflow in identifying viable siRNA candidates for broad-spectrum antiviral applications. The validation of these siRNAs supports the potential of this workflow to contribute significantly to the development of treatments for dengue and other viral infections, aligning with the goal of creating cost-effective and widely available therapeutic solutions. The ideal use of this workflow is as a commonplace tool for scientists to use when pathogens emerge to rapidly design antivirals that they can then quickly validate. If this research becomes commonly used, first of all, bad actors will have less reason to even try developing engineered pathogens due to this workflow acting as a treatment generation method to quickly neutralize their agents. Secondly, there will be a general reduction in morbidity and mortality thanks to widely available broad spectrum treatments. Finally, treatments will be able to be swiftly developed for any emerging engineered/natural pathogens, quickly reducing the dangers that they pose. And so overall, the future of this research seems very promising. In terms of next steps, the first step I'll take after the conclusion of the fellowship will be reaching out to those with the ability to validate the results of this workflow in the wet lab. Higgy and Islam's research was a major inspiration for this work, so reaching out to them with these results may inspire their own future research with computational antiviral design, advancing this field even further and establishing the workflow with accredited individuals. I'd also like to explore the efficacy of the workflow in targeting different types of viruses. Dengue is an ssRNA virus, and while the principles that went into designing this workflow scientifically will apply for all types of viruses, verifying this further would still be very valuable in supporting the broader usage of this project. And so, with that, we've concluded my presentation for the Non Trivial Fellowship. It's been wonderful working with you all in this cohort. Thank you all for listening.